Hello, this is your instructor Richard Collins. Welcome to Air Masses, Fronts and Cyclones, Unit 12 of ATM101, Weather and Climate of Alaska. This unit finally explores the features of the weather as we think about weather systematically. Before we begin, we note that our interest in weather systems focuses on cyclones rather than anticyclones. That's because cyclones are storms. In this unit, we will investigate air masses and how they form, how air masses form fronts and their weather, cyclones and how they form, mature, and decay, and cyclones and their weather. This lecture supplements our textbook Weather: A Concise Introduction by Gregory Hakim and Jerome Patou with material from the textbook Meteorology Today by C. Donald Ahrens. An air mass is an extremely large body of air whose properties of temperature and humidity are relatively uniform in any horizontal direction at any given altitude. Air masses may be hundreds to thousands of kilometers across. A cold air mass over the lower 48 on the 24th of December 1983 is shown in the lower right. The air mass is associated with a high pressure system. On the following day, Atlanta, Georgia was colder than Fairbanks, Alaska. On the 24th of December, on the edge of the high over Pennsylvania, there are clear skies with a temperature of 10 degrees Fahrenheit, a dew point of 5 degrees Fahrenheit, giving a relative humidity of 78% and a partial pressure of water of 0.2 hectopascals. Near the center of the high over Montana, there are overcast skies with a temperature of minus 30 degrees Fahrenheit, a dew point of minus 39 degrees Fahrenheit, giving a relative humidity of 60% and a partial pressure of water of 0.02 hectopascals. So we can see that as we move from the edge of the high pressure system to the center of the high pressure system, we get much colder and drier. Remember, by comparison, atmospheric pressure is about 1,013 hectopascal. So these water vapor concentrations are really very small. While we discuss air masses in terms of temperature and humidity, the underlying physical property is density. Density defines if air can move in the vertical, and it is vertical motion that causes weather. At a given pressure, density increases as temperature decreases, and density increases as humidity increases. Air masses come from source regions where there are uniform and relatively undisturbed conditions. The primary example is places where there are anticyclones with light winds, such as the Pacific and Azores highs, or the polar high. Here large bodies of air can sit and adopt the environmental conditions. Over North America, we get air masses that come from the Arctic, continental Arctic or CA, the subarctic, continental polar or CP, the Pacific, marine polar and marine tropical, MP and MT respectively, the Atlantic, marine polar and marine tropical again, MP and MT, the Gulf of Mexico, MT, marine tropical, and Mexico, CT, continental tropical. These are the primary air masses we will discuss in this unit. The continental Arctic and continental polar air masses form in winter during the long nights and periods of light winds, i.e. under large anticyclones with clear skies and temperatures far south of 0 Fahrenheit or minus 18 Celsius. As air masses move, they are influenced by the temperature and humidity of their environment. Furthermore, being associated with high pressure and clear skies, they can continue to cool. Fairbanks is lucky enough that air masses traveling south from the North Slope can get colder as they travel overland toward Fairbanks. Crossing warm water, these air masses become unstable as the cold air overlies warm surface air. This causes vertical motion, cloud formation, and precipitation. As air masses cross over the Great Lakes and rise on the southern shores, they produce lake effect snow. The southeastern banks of Lake Superior, Michigan, Erie, and Ontario have some of the highest annual snowfall in the US, greater than 72 inches or 1.83 meters per year. As continental polar air masses cross the Gulf of Mexico and the Gulf Stream, they create streaks of clouds offshore and eventually thick cumulus clouds that yield heavy rain in Mexico. Fronts are transitions between air masses. Fronts are the action centers of weather, where air masses of different density meet, one air mass rises over the other, air cools, condensation occurs, and weather happens. The simplified weather map of North America shows the motion of air masses and the associated fronts. Following the fronts, we have a stationary front from A to B. At this stationary front, cold, dry continental polar air and moist, cool marine polar air meet at the Rockies. The air masses are stationary and are not moving. The Rockies form a natural barrier that often stops weather systems, not unlike the Alaska Range, from crossing to the west, and channels weather systems southeastward from the Canadian Plains into the central and southern United States. From B to C, we have a cold front, where continental polar air meets marine tropical air. The continental polar air is pushing south against the marine tropical air. From C to D, we have a warm front, where marine tropical air meets marine polar air. The marine tropical air is pushing north against the marine polar air. From C to L, we have an occluded front. This is where a cold front has overrun the warm front and is moving to the east. The winds show air circulating counterclockwise around the central low. We see snow, sleet, and rain ahead of the warm front, and rain along the cold front. The station models confirm the characteristics of the air masses. The blow-up of the weather map in the lower center shows how wind directions are different behind and ahead of the cold front. Also, the pressure contours change direction or kink at the front. Finally, again the station data highlights the cloudiness on both sides of the front and the change in humidity with warmer, more humid air ahead of the front. The cartoon on the lower left shows the Arctic and polar fronts. The Arctic front is the transition between the continental Arctic and continental polar air masses. The polar front is the transition between the continental polar and typically the marine tropical air masses. Notice the bullnose profile of the cold dense air at both fronts and the fact that the Arctic front lies closer to the ground than the polar front. Finally, the theoretical work that underlies modern meteorology was developed by a group of Norwegian scientists in the early 20th century, with the seminal work by Bjerknes published in 1919. These scientists were influenced by the movements of armies and fronts in World War I. Weather maps with their fronts, arrows, and associated jargon mimic the military maps of that period. The book All Quiet on the Western Front, in German, Nothing New in the West, was published by Remarque in 1928 and highlighted the physical, mental, and other trauma of the war. Not surprisingly, it was banned and burned by the Nazis in the 1930s. Stationary fronts mark the boundary between two air masses that meet but are not moving. The front is denoted by a combination of red half circles for the warm air mass and blue arrows for the cold air mass. Wind blows along the front in opposite directions on each side of the front. The cloudiness along the front depends on the character of the air masses, as there is no vertical motion at a stationary front. Cold fronts mark where cold air masses run into warm air masses. The colder, denser air moves forward with a steep bullnose front where friction slows the air at the ground. The cold air mass pushes the warm air up over it. The rising air creates clouds and precipitation, with altocumulus and cumulonimbus clouds forming along the front. The cumulonimbus clouds are associated with thunderstorms. Further aloft, cirrus and cirrostratus clouds form and are blown ahead of the surface front as winds are stronger aloft. There is a pressure trough along the front, with a change in wind direction across the front. Given the sharp and rapid rise in the air at the front, cumulonimbus clouds and thunderstorms form. During the summer in the lower 48, dry, cold continental polar air from Canada travels south to meet warm, humid marine tropical air coming up from the Gulf of Mexico to create cold fronts across the central United States. The weather can bring severe thunderstorms with lightning and hail in the Midwest and Great Plains. Warm fronts mark where cold air recedes from a warm air mass and the warm air overruns the colder air. Unlike the abrupt bullnose profile of a cold front, which extends about 50 kilometers, the profile is now sloped and spans several hundred kilometers. Warm fronts move at about half the speed of cold fronts. Behind the front, it is warmer and more humid with some stratocumulus clouds. In front of the front, as the warm humid air begins to rise, we get fog close to the ground. Then as it rises further, stratus clouds followed by nimbostratus clouds with rain and snow. The precipitation can be long-lived. As the warm air rises even further, altostratus, cirrostratus, and cirrus clouds form. Again, the cirrus clouds are blown ahead as a harbinger of the arrival of the surface front and the change of weather to come. Cold fronts move faster than warm fronts, so as they rotate around a cyclone, the cold front overruns the warm front and creates an occluded front. Cold, dense air now overruns cold, denser air and pushes warm, lighter air above the cold air. The sector of warm air at the surface is pushed upward over the cold air and disappears at the surface. Similar to the geometry of the warm front, clouds form and precipitation occurs along the front. In the big picture, cyclones are the eddies that transfer heat poleward from the tropics, where there is an excess of heat, to the poles, where there is a deficit of heat. Over the course of a year, we have seen that equatorward of 38 degrees, the Earth receives more energy from the Sun than it loses through infrared emission. Poleward of 38 degrees, the Earth loses more energy through infrared emission than it receives from solar radiation. For reference, all of Africa sits equatorward of 38 degrees, from about 32 degrees north to 32 degrees south. Cities that sit near 38 degrees north and south are Auckland, New Zealand, at 37 degrees south, Melbourne, Australia, 38 degrees south, Seoul, Korea, 37 degrees north, Tianjin, China, 39 degrees north, Tehran, Iran, 36 degrees north, Murcia, Spain, 38 degrees north, Mar de Plata, Argentina, 38 degrees south, Temuco, Chile, 39 degrees south, and St. Louis, United States, 38 degrees north. The Norwegian model of a cyclone was developed in the early 1900s. The model has a 5-stage life cycle. These stages are incipient, deepening, mature, occluded, and decaying. In the incipient phase, a small disturbance appears in the isobars that we take as running mainly east-west, with cold on the north side and warm on the south side. Warm air moves poleward and rises, while cold air moves equatorward and sinks. Convergence and rising air cause cloud to form poleward of the warm front. As the cyclone deepens, the central pressure falls and the central low is enclosed. The warm and cold fronts are far apart, with a wide warm sector between them. In its mature phase, the cyclone is fully developed, with clear kinks in the isobars at the fronts and a comma pattern of clouds visible from satellites. In the occluded phase, cold air wraps around the central low, overrunning the warm front. The warm sector is detached from the central low. In the decaying phase, the central low decays and fills in. The life cycle lasts 2 to 6 days. However, two questions remain. How does the initial disturbance appear, and which cyclones become full-blown storms? To answer what contributes to a strong cyclone, we need to look at the vertical structure of these weather systems. In a mature cyclone, the central low pressure tilts westward, while in the occluded cyclone, the central low pressure stacks vertically or tilts eastward. Aloft at 300 hectopascals, about 9 kilometers, the flow between isobars changes speed as it flows eastward. In the ridges, the flow is faster than in the troughs. In between the ridges and troughs, geostrophic balance holds and the flow is geostrophic. The faster flow is supergeostrophic and the slower flow is subgeostrophic. So we have air piling up or converging at C as it slows down approaching the trough, and air thinning out or diverging at D as it speeds up leaving the trough. As a result, air falls at C and rises at D. The 300 hectopascal level is near the tropopause, and above the tropopause the stratosphere is very stable and air does not rise easily. If the divergence D lies above the surface cyclone, it will deepen, as the divergence aloft supports convergence and rising air at the surface. So the optimum position for the cyclone is to have the surface low located to the east of the trough. Similarly, the surface anticyclone sits to the east of the ridge. Eventually, the trough moves over the low and the cyclone fills in. The winds die out due to friction. The scheme where the jet stream aloft supports the surface high and low is shown in the two top cartoons. The figure in the right provides more detail about the typical weather associated with the weather features. Cyclones need divergence aloft, rising air, and surface convergence. Anticyclones need convergence aloft, falling air, and surface divergence. The ridge and trough sit to the west of the surface high and low respectively. If the ridge and trough move eastward over the surface high and low, the falling and rising air are no longer supported, and the anticyclone and cyclone decay. Over their life cycle, the cyclone has done its job, moving warm air poleward and cold air equatorward. Let's examine the life cycle of our favorite 2014 cyclone. This storm produced thunderstorms and tornadoes across the United States, as well as 6 to 10 inches of snow in southern Minnesota and 12 to 15 inches in northern Minnesota. In the upper left, we have the upper air chart at 500 hectopascals, about 5,300 meters, with isobars and wind barbs. The black circle is the location of the surface low. In the lower left, we have the surface isotherms and isobars. In the upper right, we have the visible satellite image with surface isobars. In the lower right, we have station model winds, precipitation, and isobars. In this slide, in the incipient phase, we see a weak trough aloft and a surface low to the east of it. There are small cold and warm fronts around the surface low, with the trough extending northward from the low. The satellite shows cloud to the north of the warm front, but few clouds at the cold front. The stations report rain ahead of the warm front. 12 hours later, in the deepening phase, the trough has deepened aloft, wind speeds have increased, and the surface low is still to the east of the trough. The surface shows a well-formed low-pressure system with a central pressure less than 992 hectopascals. The fronts are better defined with sharper temperature gradients, and there are kinks in the isobars at the fronts. The northern low has merged with the central low. The satellite shows more clouds, with clouds now forming along the cold front. The stations report more rainfall ahead of the warm front, snowfall over Minnesota, and rain beginning along the cold front. Tornadoes were recorded on this day in Illinois. 12 hours later, in the mature phase, the trough has deepened further. The trough has now moved closer to the surface low. The surface low now has a central pressure of less than 980 hectopascals. The surface low is occluded with warm air along the occluded front. The kinks in the isobars along the cold and warm fronts are more obvious. The satellite shows the clouds aligned with the cold front. The stations report rainfall ahead of both the cold and warm fronts. 12 hours later, in the decaying phase, the central low pressure aloft now overlies the surface central pressure. The surface central low pressure remains below 980 hectopascal. The low pressure is fully occluded. The cold front has extended and detached from the central low. The satellite sees a classic comet cloud aligned with the occluded and cold fronts. The stations report winds that encircle the surface low, with rain along the cold front. The upper level geopotential surfaces at 500 hectopascal, about 5,400 meters, and 300 hectopascal, about 8,900 meters, provide additional insight into the upper level support for this storm. In an undisturbed atmosphere with no weather, the contours would be perfectly circular and concentric with no ridges or troughs as shown in the upper right. The real-world contours meander, forming ridges and troughs. The ridges and troughs are formed by large-scale atmospheric waves called planetary waves, traveling around the globe. Long waves have several peaks, ridges, and valleys, troughs, as they go round the world over the course of days to weeks. Short waves are superimposed on the pattern and travel much faster. They superimpose on the long wave pattern, deepening and weakening the ridges and troughs. During the February storm, the pattern is far from textbook, but there is evidence for short waves crossing the lower 48 and contributing to the formation and maintenance of the February storm. Where do cyclones come from? The creation of cyclones is called cyclogenesis. The maps show storm tracks over 7 years in the north and southern hemispheres. In the northern hemisphere, there are two permanent troughs of low pressure over the western Pacific and western Atlantic, where storms tend to originate. These storms travel eastward across the ocean basins as they mature. In the northern hemisphere, the storms meander north and south as they travel from the oceans to the continents and back to the oceans. In the southern hemisphere, the storms follow a more regular path over the ocean. There are areas of cyclogenesis southeast of Australia and southeast of Africa. However, cyclones are also generated by high mountains such as the Rockies and Andes. These mountains run north-south at right angles to the predominant westerly winds. On passing over the mountains, the wind is deflected toward the equator due to some complex rotational physics we will skip over, and forms a trough with low pressure on the lee side of the mountains. Depending on the winds aloft, this trough may contribute to the formation of a cyclone. Thus, there are areas of cyclogenesis in the lee of the Rockies and the Andes. North of the polar front, small intense cyclones form. These are called polar lows or Arctic hurricanes. A most beautiful polar low was observed by satellite on the 26th-27th of February 1987. The image of the storm with hurricane-like eye captured the attention of meteorologists. A more recent polar low formed over Siberia in early August 2012. The storm moved over the Arctic Ocean and deepened to a central pressure of 967 hectopascals. These storms with near hurricane central pressures are major storms with high winds and snowfall. Fortunately, the systems do not have hurricane winds. The Coriolis force increases with both latitude and wind speed. So at high latitudes, the Coriolis force required to balance a given pressure gradient force needs weaker winds than at low latitudes. Finally, our summary and takeaways for Unit 12 are: 1. Air masses are characterized by their density, due to their temperature and humidity, and define weather events such as cold air outbreaks that are associated with continental Arctic air masses. 2. Fronts are the boundaries between air masses of different densities. 3. Stationary, cold, warm, and occluded fronts all have specific weather patterns based on how air masses rise over each other. 4. Cyclones attract more interest than anticyclones because they are storms. 5. Cyclones provide the physical mechanism to transfer heat from the tropics to the poles. 6. The Norwegian model provides a framework for understanding the life cycle of cyclones, where they are initially formed along fronts. 7. The upper air conditions with convergence and divergence aloft are critical in supporting the formation and persistence of cyclones. 8. Rising air with release of heat is important in supporting the development of cyclones. 9. Polar lows are intense forms that form over water in the extremely cold air of polar regions. Thank you for your attention.